Well, hello, welcome again to Math 315, Analysis and Topology, and this is the last chapter for this course, section 10, where we're going to look at some topology. I mentioned before, chapters 9 and 10 are probably the most difficult of the two chapters here, and again I'll be fairly explicit in the tutorial problems as to what sort of things I'm expecting you to be able to do, but it's good if you can just follow through the mathematics here and try and get some idea of what we're talking about. So we turn now to the subject of topology, which is part of the name of the course. We've been doing essentially analysis and little bits of topology, but we're moving now to the last part. Roughly speaking, topology is the study of the geometric ideas behind analysis. That is, ideas that do not depend on length, size, or magnitude. So I've been using lots of absolute values and things and measuring sizes and distances and things when we looked at sequences and functions and so on. Topology tries to get behind that and look at the geometric underpinnings and try and see the most basic, fundamental underlying ideas of analysis. So we're going to look at properties that do not change under continuous transformations. There are many branches of topology. You may have come across some of these already. It's combinatorial topology. We're going to be concerned here with what is generally known as point set topology. And this goes back to the early 1900s, in fact. So in much of what follows, we're going to be looking at the real line or the plane. But the idea is we have generalized to any number of dimensions, and in fact we will see later we can abstract the whole thing off to what's called a topological space. Now the first key idea, and an important idea, is that of an open set. The concept of open set is one of the topics in the syllabus for this course, and so we need to come to grips with that, what we mean by an open set. So we firstly define what's called an epsilon neighbourhood, and this is a way of measuring closeness. So as before, we look at this notion of closeness, what we mean by points being close. So here's our definition: a neighbourhood, also called an epsilon neighbourhood, of a point A on the real line is a set of this form. All it means graphically, if I draw a little picture of this, all it means is there's our real line, there's the point A. We're going to draw a little epsilon band, and I go A minus epsilon. We're going to go back a little way, and we're going to go forward a little way. And my x is such that the distance between x and A, so there's my x, that distance is less than the width of the band, less than epsilon. So you've sort of seen this idea before when we've talked about epsilon bands and things. This is called an epsilon neighbourhood. And we're going to use this notation n of A epsilon. So A is the centre of the epsilon neighbourhood, and epsilon is how wide it is. Now notice it's a strict inequality here, so that means this is an open interval on the real line. This is an open interval. So for example, if I take n 3, 0.1, then that means there's 3. I move forward 0.1, I move back 0.1, and I take this open interval in here. And this is simply the open interval between 2.9 and 3.1. And that's going to be called the epsilon, the 0.1 neighbourhood of 3. Now, we can extend this idea to the plane, and in this case, an epsilon neighbourhood is going to be a dotted circle, and open the interior of a dotted circle, centre A, radius epsilon. So if we're talking about the plane, the xy plane, then we can think that we could use the same definition, except now we're thinking of x as a vector and A as a vector, and this is just measuring the distance between x and A, and that's got to be less than the width of the band. And so an epsilon neighbourhood on the line looks like an open interval. In the plane, it looks like an open disk. And in 3 dimensions, the epsilon neighbourhood of a point, A, would simply be the interior of a sphere, centre A, radius epsilon. And for this reason, it's sometimes called an open ball. But I'm not going to use that word here very much. We're going to talk about just epsilon neighbourhoods. Now, on the real line, every epsilon neighbourhood just consists of some open interval. So PQ, and the centre of it, well, we just take the average of P and Q. That's P plus Q on 2. So that'll be the centre of the epsilon neighbourhood. And the epsilon neighbourhood is just going to consist of some open interval between P and Q. And that's what we mean by an epsilon neighbourhood. Now we need this notion of epsilon neighbourhood in order to define what we mean by an open set in a moment. So the above definition simply says that we're looking at the set of all points that are in some sense close to the number A. In some sense close to the number A. They're within epsilon of the number A. In some situations, we want the set of points close to A, but we don't want to include A itself. And this is called a deleted neighbourhood. So it's the set of all points that are close to A, but we're excluding the number A itself. And here's the definition of it. The deleted neighbourhood of a real number A is this set, and we put a star up here to indicate it's a deleted neighbourhood. And it's exactly the same as before, except now we say that the absolute value of x minus A is strictly bigger than 0, and that means this first inequality ensures that we exclude the number A from the set. So graphically, again, this set simply looks like this. So this time we're excluding the point A, so put an open circle there. We want all the points that are between A plus epsilon and A minus epsilon. But it's an open interval, so we're excluding the 2 endpoints, and we're also excluding the point here. And that's called a deleted neighbourhood. Now, armed with that idea, we can then define what we mean now by an open set. And this is a subtle idea. It turns out to be absolutely very central to topology, and very, very crucial to analysis, in fact, in general, the idea of an open set. It's one which turns up in complex analysis as well. When one's looking at analytic functions, it's a very common concept in mathematics. So a subset A of real numbers is called an open set if, for every A inside the set, you can build an epsilon neighbourhood of A, you can construct some epsilon neighbourhood of A, which lies completely inside the set A. Now, in very loose language, I often use this funny analogy. A set is open if there's enough room to swing a cat, provided the cat is small enough. Apologies here to cat lovers. The reason I say swing a cat, because this makes more sense when we're looking in 2 dimensions, as we'll see in a moment, but every open interval, for example, is an open set. So if I give you some open interval, then if you pick any point inside the open interval, then you can just squeeze in a little epsilon neighbourhood. And that epsilon neighbourhood stays inside this interval. You can go very close. For example, I could take a point B here, which is very close. Remember, the endpoints are excluded, so we can't include the endpoint here, and you can just squeeze in a little epsilon neighbourhood around that point. Notice by comparison, if I've got a closed interval, just by comparison, if I now take a closed interval, say AB, then okay, if I'm at a point here, there's enough room to swing a cat. You can put a little epsilon neighbourhood here, but this includes the 2 endpoints. So if I were to take the point B itself and try and put a little epsilon neighbourhood in here, then a little bit of it's going to go outside of the interval. So this set here is not open, because at the point B, there is not, you can't put an epsilon neighbourhood at the point B, which is included in the set this time, because we're including the two endpoints. Same at A. If I tried to put a little epsilon neighbourhood here, it would go outside of the set, so this is not an open set. So that's the difference between the two. In two dimensions, a typical open circle, so the inside of an open circle here, with excluding the boundary, this is an open set, because again, if I pick a point inside the set, then I can just squeeze a little epsilon neighbourhood. There's just enough room to swing a cat, and I stay inside the open set. On the other hand, if we compare that with a set which is not open, suppose I take a circle including the boundary this time, so I'm taking the inside of here, but including the boundary, then of course if I'm at a point here, there's enough room to swing a cat, there's enough room to put a little epsilon neighbourhood, but this includes the boundary, so if I take a point on the boundary, then as soon as I put a little epsilon neighbourhood, then part of that will go outside of the set. So this set is not open. There's not enough room to swing a cat at that point on the boundary. Well, the first little example here is to explain why the open interval 0, 1, more formally, is an open set, to give a sort of more detailed proof of the fact that 0, 1 is an open set. So here's our interval 0, 1. If we take a point, so I've got to be able to put an epsilon neighbourhood at any point. So if I pick a point A in here, if A happens to be between 0 and a half, then how big an epsilon neighbourhood can I take? Well, I can simply take I can make epsilon to be A over 2. So A over 2 will be half that length. So I'll move back a little bit and forward a little bit, and I'm inside the set. So in that case, I could take epsilon to be a half of A, and then there's my little epsilon neighbourhood n of centre A, radius a half A, radius epsilon. That's contained in the interval 0, 1. On the other hand, if I take an A between a half and 1, then what will I do? Well, again, I'm just going to measure half the length here with this. So I'm going to take 1 minus A, that'll give me the length in here, take a half of that, divide it by 2, and then if I move that way and I move this way, that little epsilon band is still inside the set. And so again, I can take an epsilon neighbourhood centre A, radius 1 minus A on 2, and that'll be contained inside the interval 0, 1 as well. So there's a more formal proof, if you like, this particular set is an open set. So roughly speaking, the set is open if at every point in the set you can draw an epsilon neighbourhood that stays inside the set, or more graphically, there's enough room to swing a cat. So as we saw in that example, in either case, whether A is between 0 and a half, or whether it's between a half and 1, we have an epsilon neighbourhood of A that's always in the open interval 0, 1. On the other hand, if we take the interval, the closed interval 0, 1, this is not an open set. And let me just again go through a little explanation of that. So this is not open since, well, there's my interval. The point 0 belongs to A because it includes the endpoints. But as soon as I put an epsilon neighbourhood around 0, so no epsilon neighbourhood with centre 0, radius epsilon for any epsilon is completely contained in A, because part of the epsilon neighbourhood will go outside of the interval, and therefore this is not an open set. Also, the circle with the boundary included is not an open set, as we mentioned before. And here's a little explanation of this again. Just got to write some words out to explain it. So the set A now, all the points in the plane where x squared plus y squared is less or equal to 1. So that's this set here containing the boundary. Now A again is not an open set, since the point 1, 0, and I could have picked any point on the boundary, but it's sufficient just to pick one point, so I'll pick the point 1, 0 on the boundary. This belongs to A, it satisfies the condition, but as soon as you draw an epsilon neighbourhood around here, then you're going to move outside of the set. So no epsilon neighbourhood n of the centre 1, 0 radius epsilon. Put a comma there. Normally no epsilon neighbourhood is completely contained in A. So that set will not be an open set. Just to finish this little section, we note that not all open sets on the real line have to be bounded open intervals. So for example, the unbounded interval 0 to infinity, which looks like this, so we exclude 0, we take everything further on. This is also an open set because I pick any point inside here and there's enough room to swing a cat. And we're not including 0, so there's no problem there. We can go as close as we like to 0, but no matter how close we go to 0, I can just squeeze in a little epsilon neighbourhood by taking epsilon to be half the distance of that point to the origin. Also, the union of open intervals is also an open set. So if I take this open interval and then I union that with 1, 2, in fact, I probably, what have I done here? This is a bit, that 1 is this same one here. It would have been more sensible, in fact, now that I think of it, I'll change this in the notes to make this say 2, 3. So we've got a fair dinkum union. So we've got the union of these two sets, the union of the set from 0 to 1 and union of the set from 2 to 3. This is also an open interval, got a union of two sets. So either the set consists of all the points in here plus all the points in here. And again, at each point inside the set, there'll be enough room to swing a cat. If I pick a point here, there's enough room to swing a cat. These two sets are in fact disjoint, but their union is an open set. And we'll come back and have a look at that in more detail in the next recording.